Okay, for the first several videos that we've looked at differential equations, we've looked at several different methods for solving first order linear differential equations, first order Bernoulli nonlinear equations, and separable equations, differential equations. And in this video, we're going to recap those methods, at least in a general sense, for how to solve them. And we're going to introduce a new method for looking at what we call exact differential equations for multivariate equations. Those are equations where we have to do implicit differentiation. So, without any further ado, we're going to look at in the first type, what we have done up until this point in time.
Okay, in the first type, it's a first order linear of the form that takes y prime plus p of x y equals g of x. And this solution wasn't proven up to this point. They said the proof was lengthy and they saved it to the end of the section. We haven't gotten to the end of that section yet. So we take it that x is continuous on some interval, and that x0, any initial condition that we may have, is within this interval, and that we have some function y equals f of x as a solution, and y0 is the initial condition that we can solve for the constant c. So in this case, we were given that y of x is given by the solution 1 over mu of x times mu of x times g of x dx plus c over mu of x. And that's pretty straightforward. We did quite a few problems using this method, and we were given that mu of x is equal to e raised to p of x dx, and that when we find the solution, we can solve for c when we have y of x0 equals y0. So c is going to equal to the y0. Now in our second case, we're looking at nonlinear forms. Nonlinear first order differential equations, and they're a special type of first order nonlinear, this is our second case, called Bernoulli Equations. And these take the form of y prime. Of course, y prime is simply dy dx. Again, that we're not talking implicit equations. We're talking about normal single variable, one dependent and one independent variable, where x is continuous on some interval and x0 is within that same interval, and that we assume that y of x is given as a function of x. So the equations that we looked at were plus p of x, y equals, let's say, q of x, y to the n, where n is greater than 0. Greater than 1. Because when y is 0, then y to the n is 1, and when n is 1, then we have y. When n equals 1, then we have y. So that would be the linear case, and in both situations we wouldn't have a nonlinear. It has to be n greater than 1. And in this case, we have a substitution that was found by Gottfried Leibniz. My former boss was Gottlieb. Gottfried Leibniz. And so it's a Leibniz solution. We call this a Leibniz substitution, where v equals y to the 1 minus n. And by doing so and making this substitution, we then convert the equation into a linear. So it's transforming into a linear diffq. And then we solve just like a linear differential equation, and we have v equals 1 over mu of x times mu of x q of x dx plus c over mu of x. And when you find the solution, you have to transform that back into y. So we have v to the 1 over 1 minus n equals y. And so the solution is y of x is 1 over mu of x, mu of x, q of x dx plus c over mu of x 1 over 1 minus n. And that's the solution back to y of x. Now we then moved into multivariate forms, And we called these separable. That was the third case. Separable equations, where we have, let's see what we got here. Nonlinear. We looked at nonlinear. So here's separable, where we start out with, we assume that the differential, ui dx, is some function of x and y. It's not a single variable function. And in this case, we're given m of x and y plus n of x and y dy dx is equal to 0. And that's the form these equations take. And in solving them, we have n x of y dy dx is equal to minus m of x and y. It could be the other way around. It doesn't really matter. And when I say the other way around, this could be positive and that could be negative. And in this case, we then have minus n of x y dy is equal to m of x and y. I'm sorry. In our third case, we have separable equations. And in this, we assume that dy dx is a function of both x and y. So, in the beginning, we have a function m of x and y plus n of x, y, dy, dx is equal to 0. That's the form that we're taking. Again, we're talking about continuity on some rectangular area where x is continuous between some interval b to a, and y is continuous on some interval d to c, and that x0 and y0 lie within this domain. Now, in solving these, we find that where we may be able to find that m is a function of x only, and n is a function of y only. So in this case, we have mx equals minus n of y dy dx, but then we have m of x dx equals minus n of y dy. And in this case, we assume that there exists some function, h1 and h2, h1 and h2, such that the derivative, h1 of x, is equal to m of x, and h2 prime of y equals n of y. So then we end up with the equation h1 prime of x plus h2 prime of y dy dx is equal to 0. And we assume that some function y is equal to some function of x and is differentiable function of x. So we have h2 prime of y dy dx is equal to d dx of h2 f of x. And so then we put that back into the equation. We have h1 prime of x plus d dx of h2 of f of x, and this is equal to 0. And we can take d dx out, and we got h1 of x plus h2 of f of x equals 0. And then we have h1 of x plus h2 of f of x equals a constant. And then we can solve for c. We can solve for c if we have y of x0 equals y0, then c is equal to h1 of x0 plus h2 of y0. So that is pretty much what we covered with separable equations. We looked at a number of examples. It's being able to bring the proper variable to the differential and separating them out such that we're able to take the differential, the integral, and just quickly, there was a lot to that. We'll just look at quick refresher sample or example. We have 3x squared plus 4x plus 2 minus 2y minus 1 dy dx. So if we bring, this is m and this is n, and you can see here it's a very simple situation that if we have minus 2 of y minus 1 dy dx is equal to minus 3x squared plus 4x plus 2, and now we have, well, we can make this positive, 2 times y minus 1 dy, and we could make this 3x squared plus 4x plus 2 dx. And then we just integrate, and we have dy equals 3x squared plus 4x plus 2 dx. And this gives us y squared minus 2y equals 1/3. Whoops, I'm sorry. That gives us x to the third plus 2x squared plus 2x. And now we have a constant plus some constant. And if we really want to, we can make this we can use the quadratic formula to solve this for the constant. I mean, we could do that, or we could say that we have, in this case, y of x0 equals y0. So are we given a condition? Yes, we are given that y of 0 equals minus 1. So if we bring this across, we have a big, long quadratic equation. We've got y squared minus 2y minus x cubed plus 2x squared plus 2x minus or plus c equals 0, and then y would be equals 1/2, but that's 1 because there's a 2 there. 1 plus or minus 1/2 square root of 4 minus 4 times negative x cubed minus 2x squared minus 2x minus c. And with this, we can put in y of 0 is equal to minus 1, and that's equal to Well, these are all 0, so we have 1 plus or minus 1/2 4 minus 4c, and we can bring the 4 out, and that gets rid of the, so we got that plus or minus 1 minus c, and you square that, so 1 plus 1 minus c, 1 plus 1 minus c. You can see it gets a little complex, but we end up with c equals 3 when we're done with this. And then the final function, y of x is equal to 1. And in this case, we have to make a decision between a positive and negative solution. But that would be the solution in this case. So that's just how separable equations are looked at. Then we looked at, that's the third case, and now we're on our fourth circumstance called exact equations. Okay, exact equations. This is our fourth method that we're given. So we have a function, let's say my plus n of x y dy dx equals 0. We have an equation of that form, and I'm going to move myself out of the sun. In this case, we're not looking to find m or n as dependent on a single variable, x or y. Again, the functions need to be continuous on some rectangle where x is continuous on some interval and y is continuous on some interval, and we can now look at this situation. Now, we say that m of x, y is some partial, the result of some partial differential of equation, or differential of some function, dx of some function x and y, and we say n of x and y is the differential with respect to y of the same function x and y. And so, if the equation is exact, we find that, whoops, I don't know what happened there. Okay. I hate it when that screen moves like that. Okay, so if we have an exact equation, we find that dy of dx of f of xy is the same as dx of dy of the same function. So this means if we differentiate m with respect to y, it should be equal to the differential with respect to f of n of x, y. And that's the basis for the method. And if this is the case, then the equation is exact and there's a solution. And the trick is coming down to finding what that solution is. And so we say that f of x, y is equal to m of x and y dx plus some function of y. Now, the reason we say that, this takes the place of c. So h of y is analogous to the constant c. And the reason for that is because we've already taken a differential with respect to y, and we're looking for some solution as a function. It's not going to be just a constant, it's going to be a function. And that function, h of y, is found by h prime of y is equal to dy of m of x and y dx. Oh, I'm sorry. I gotta be more careful. This is h prime of y equals n of x, y minus this. So now we have the two conditions. And that's how we solve these equations. So let's go through this again. We have a function m of x, y plus n of x, y dy dx equals 0. And if dy dy of m x and y is equal to d dx of n of x and y, then it's exact, and there's a solution, and the solution is found by this. And h prime of y is equal to n of x, y minus d dy m of x, y dx, and that's it. So that's our method for exact equations. And then once we have the solution, then it's all equal to C. So we have the solution is given by this, and then we can y of x0 equals y0 and solve for the constant. So let's take a look at some. There are a number of these that we can do. Some of them can get pretty complex, and that's time consuming. So here we go. Let's start out with this one. We're starting out with y cos x plus 2x e to the y plus sine x plus x squared e to the y plus 2 y prime equals 0. So this is m and this is n. So if we go d dy of m, that's equal to cos x plus 2x e to the y. If we take the differential of n with respect to x, we got sine of x plus x squared e to the y plus 2. And that's equal to cos x plus 2x e to the y. So, since these two are equal, we have an exact equation. And now we can solve for f of x, y is equal to y cos x plus 2x e to the y dx plus h of y and this is equal to y sine of x plus x squared e to the y plus h of y. Now we have to find h of y. So h prime of y is equal to nx, so that's sine x plus x squared e to the y plus 2 minus dy of m y cos x plus 2x e to the y dx, but we already took that differential, so that's equal to sine of x plus x squared e to the y plus 2 minus cos x, or minus sine x. There we go. Yes, that this differential is that, so we have to integrate that part, which is sine of x plus x squared e to the y, and these cancel, and we're left with h prime of y equals 2. So y, h of y, is equal to 2y. And then our solution is y sine x plus x squared e to the y plus h of y, that's 2y, equals a constant. And I don't think that there was any given differential equation for that. Was there an initial condition? No. So we don't solve for C. Now, here's another example. Here we go. I'm just going to get myself in order here a second. I don't want to get my papers out of order. Okay, here's our next example. Three x squared plus 2xy plus x plus y squared dy dx is equal to 0. So this is our m, and that's our n. And if we go dy of 3x squared plus 2xy And is that equal to d dx of x plus y squared? Is that the case? Well, let's take a look. d dy is 2x, and d dx is equal to 1. So these do not equal each other and not exact. And so no solution. And what happens if we do try to solve something like that? What happens? Well, let's try and carry that out. Let's see what results. F of xy would be given by 3x squared plus 2xy dx plus h of y. Remember, it's got to be a homogeneous function of y. And if we take this integral, we've got x to the third plus x squared y plus h of y. H prime then of y would be given by n, so x plus y squared minus d dy of 3x squared plus 2xy dx, and that's equal to 2x dx is equal to x squared. And we end up with x plus y squared minus x squared. And that's not a function of y, because we have values of x. It's a multivariate function. So there's no solution. Yeah, you can hear it's starting to get noisier now as the sun rises higher. Okay, so we're given a bunch of problems, and maybe we can solve a number. There are some here that are quite involved, quite difficult, because it requires techniques of methods of integration that we've learned in the past. So here, let's try this one. This is a simple one, 2x plus 3 plus 2y minus 2 dy dx is 0. So let's go d dy of 2x plus 3, and that's 0. d dx of 2y minus 2 is also 0. So these are exact. They're the same. So there's a solution. So we can find the solution by this, and this is equal to x squared plus 3x plus h of y, and h prime of y is equal to n of x, 2y minus 2 minus d dy of 2x plus 3 dx, but that's 0. Y minus 2 And so, because this is 0, so we have h prime of y is equal to 2y minus 2. So h of y is equal to y squared minus 2y. And our solution then is x squared plus 3x plus h of y, so that's y squared minus 2y, is equal to a constant. And that's our solution there. That was a simple one. As we progress, these things will become increasingly difficult. So, that was our first problem. And the second one is similar, but we got to be careful. So 2x plus 4y plus 2x minus 2y dy dx is 0. dy of 2x plus 4y is equal to 4, and dx of 2x minus 2y is equal to 2. And 4 is not equal to 2, at least as far as I know, and so there's no solution. And if you carry this out, you'll see that h prime of y is equal to some mixed function of x and y, and it has to be a function of y. Exclusively of y. So that was a simple one. There is no solution to that one. It's a nice test to see whether or not a differential equation, multivariate, has a solution. So here we've got another problem, 3x squared plus 2xy plus, we looked at this one. That one we already looked at. I don't know why I have it down twice. Sorry about that. Alright. I don't know why I wrote that one down twice. Okay, here's a little more complex one. It's only by virtue of it being a bigger polynomial. 9x squared plus y minus 1 plus or minus y 4y minus x dy dx is 0. So we can rewrite this to 9x squared plus y minus 1 plus x minus 4y dy dx is 0. And now we take our differentials. dy of 9x squared plus y minus 1 is equal to 1. dx of x minus 4y is equal to 1. So they're exact. And so there's a solution. So we can say that f of x and y is given by 9x squared plus y minus 1 dx plus h of y. And then this is equal to 3x cubed plus xy minus x plus h of y. Now all we have to do is solve for h of y. So h prime of y is equal to let this screen straight. Sorry about that. Is equal to n, which is x minus 4y minus dy of 9x squared plus y minus 1 dx, and this is equal to x minus 4y minus dx is equal to minus 4y. So h prime of y equals minus 4y, and h of y then equals minus 2y squared. Then our solution is 3x cubed plus xy minus x minus 2y squared equals a constant. And this is our solution. Still not too bad. We're dealing with polynomials of variables x and y. Let's see. There are 11 of these problems, so I don't want to waste much time moving on. This one is a little longer. This is the fourth example. 2xy squared plus 2y plus 2x squared y plus 2x dy dx equals 0. So now we do our differentials, partial differentials, dy with respect, differential with respect to y of 2x y squared plus 2y, and that's equal to 4xy plus 2, and dx of 2x squared y plus 2x is equal to 4xy plus 2. So they're exact. And there's a solution. So what we do, we've got we've got 2xy squared plus 2y dx plus h of y, and that's equal to x squared y plus 2xy plus h of y. Now we solve for h prime. h prime of y is equal to 2x squared y minus or plus 2x minus d dy of 2x y squared plus 2y dx, and this is equal to 2x squared y plus 2x minus 4x y plus 2 dx, and this is all equal to 2x squared y plus 2x minus 2x squared y minus 2x, and that's 0. So our solution then has already been found. It's x squared y plus 2xy equals c. And that is our solution. That was my best box. All right. Let's look at another. That was the fourth example or exercise in the book. Here's an interesting one. We're given dy dx equals minus ax, make sure I write it right, plus by over bx plus cy. We do a little manipulating. We have bx plus cy dx, or dy dx equals minus ax plus by. Bring that over. We've got ax plus by plus bx plus cy dy dx equals 0. And now we do our differentials. dy of ax plus by is b, and dx of bx plus cy, and that's equal to b, and so they're exact. So now we do our integration. For the, plus h of y, and this is equal to a over 2x squared plus bxy plus h of y. All right, so now all we have to do is find h of y, and so we have h prime of y is equal to d, so bx plus cy minus dy of ax plus by dx, and that's equal to bx plus cy minus, now this is bx. And so we're just left with cy. So h prime of y is equal to cy, and h of y is equal to c on 2y squared. And now we write our final solution. We got a on 2x squared plus bxy plus h of y, which is c on 2y squared, is equal to some constant. And we can always multiply through by 2, so we have x squared plus 2b ax squared plus 2b x y plus c y squared equals some constant prime. And that's it. That's our solution. And I don't know if I can draw a good rectangular box, but I'll do my best. So, that's it. You can see these things getting progressively harder. There was one that took me 4 sheets to do. Now here's one that is similar to the one we just looked at. dy dx is equal to minus ax minus by and bx minus cy, and this is then ax minus by plus bx minus cy dy dx is 0. And if we take our differentials, partial differentials, dy of ax minus by, that's equal to minus b, and we have dx of bx minus cy is equal to b. But negative b is not equal to b, so we're not exact. And there's no solution. To this problem. You could carry it through to show yourself that h prime of y is some function of x and y instead of the required f of y. But we won't do that here. It's just extra motion. Why go through all that trouble if there's a known solution? Now, here is one that is a little more interesting. We got e to the x sine y minus 2y sine x dx plus e to the x cosine y plus 2 cos x dy. Now you may be tempted to just want to integrate at this point. I'm sorry, this is equal to 0. But let's go through our process. First we divide through by dx, and so we have, let's make this simpler. We divide through by dx, so that means we have dy dx over here. This becomes m, and this is our n. So dy of e to the x. Looks like we got a b in the house. Sine y minus 2y sine x. And we have dx of e to the x cosine y plus 2 cos x. And let's see what we have here. So d dy, we have e to the x cosine y minus 2 sine x. Is that equal to this? Let's see. D dx is e to the x cos x, or cos y. So far, so good. Minus 2 sine x. So we have an exact equation, and we have a solution for that. So let's look at f of x, y. You can see these are getting a little more complex. E to the x sine y minus 2y sine x dx plus h of y, and that's equal to let's see, this is equal to e to the x sine y plus 2y cosine x plus h of y. Now we go to h prime of y is equal to e to the x cosine y plus 2 cosine x minus d dy of e to the x sine y minus 2y sine x dx. And with this, we end up with this. Let's take a look at that. This is e to the x cosine x minus 2 sine x dx. And so this is e to the x cos y plus 2 cos x minus, and if we differentiate, we have e to the x cos y, and that's minus 2 cos x, and that's equal to 0. So h prime of y is equal to 0, which means h of y is a constant. So our solution then is e to the x sine y plus 2y cosine x plus a constant is equal to a constant, and you can combine the constants, and we just have e to the x sine y plus 2y cosine x is equal to some other constant. And that's it. That's our solution. Now, there's one problem in particular that is going to be very labor-inducing because it involves this one. Here's one that's very, very, very involved. And I think this is the one that's going to take us a long time. Let's take a look at this. Yeah, this one's very, very, very involved. I don't know how we're going to approach this because I don't have that many sheets on the screen, but let's write it out. It's funny because the following problem is nowhere near as hard. Okay, so let's say we're given this. Y e to the xy cos 2x minus 2 e to the xy sine of 2x plus 2x plus, it says dx, but again we just divide through. I don't want to, I'm just saving space. It's really not a big deal. E to the xy cosine 2x minus 3 dy dx. Now I just want to say what I did here. This term was multiplied by dx, and so I just divided through by dx to come up with this form. Now our trick is to differentiate. So we take the partial derivative with respect to y of y e to the xy cosine 2x minus 2 e to the xy sine of 2x plus 2x. So, in the in this differential, we have to differentiate using some early techniques that we did. We're differentiating with respect to y, so we treat x as a constant. So we have e to the xy cosine 2x plus xy e to the xy cosine 2x minus 2x e to the xy sine of 2x. All right, so that's the differential for that term. Now this term, the x of x e to the xy cosine 2x, we got three variables there, minus 3 right there. So this is going to be interesting. So let's hold x out for now, and we have y e to the xy cosine 2x minus 2 e to the xy. Let's see, I don't want to make any mistakes. I'm doing it with respect to x. So 2 sine of 2x and now plus x e to the xy cosine 2x, and let's see where that gets us. We have xy e to the xy cosine 2x minus 2x e to the xy sine of 2x plus x e to the xy cosine what did I do? I made a mistake. See, this is why you got to be careful. (2x). Let's see what we got here. Yes, this term, that term, and that term are the same. This and this are the same. This and this are the same. So we have an exact equation. Now, all we have to do, and that's this is the simple part. All we have to do now is integrate for the solution. So f of xy is equal to y e to the xy cos 2x minus 2 e to the xy sine of 2x plus 2x dx plus h of y. And h prime of y is equal to x e to the xy cos 2x minus 3 minus d dy of y e to the xy cos 2x minus 2e to the xy sine of 2x plus 2x dx. And since we've already taken that derivative, then we, partial derivative that is, we have x e to the xy cos of 2x minus 3 minus, and we have e to the xy cos 2x plus xy e to the xy cos 2x minus 2x e to the xy sine of 2x dx. All right, so now it comes down to solving these integrations. Number 1 and number 2. Two integrations. And I can tell you right now what you're probably guessing, and your guess is correct, that this is going to be all that's left after we integrate. But, geez, that's a long integration. Yeah. And if you guessed that, you'd be right. I mean, intuitively. But you don't know that. That's the problem. You don't know that at this point. So you really need to go through the integrations to find out what the solution is. And so I'm gonna walk you through the process. It's going to be very tedious. So I'll just kind of point you in the right direction. You're going to need to integrate by parts. So we've got what integrations we have. This one is equal to y e to the xy cos 2x minus 2 e to the xy sine of 2x plus 2x dx. And this one, h prime of y equals x e to the xy cosine of 2x minus 3 minus dy of the other, which turns out to be e to the xy y cosine 2x plus xy e to the xy cosine 2x minus 2x e to the xy sine 2x dx. These are the integrations you need to solve. So, first off, it's best to break it up into pieces, because the top integral is really where we have f of xy. Oh, I forgot, plus h of y. The top integral, f of xy, is three separate integrations, as is the bottom integral. And we can take advantage of some knowledge from the top to the bottom. So if we look at, let's take a look. I think I did this. I think I did this one first. And so I looked at this piece, and I looked at each piece separately. E to the xy cos 2x dx. Oh, I'm getting some coffee. Thank you. I'm almost concluding. Oh, it didn't stick?
Well, I didn't quite, I just got the bot, he was moving around and I nipped him, so he was stuck on the thing and I pulled it down. Look at all those wasps.
Yeah, I gotta finish this. I'm recording right now, so it's dead time. Okay, so we take each little piece at a time. And we're looking at this first piece right there. And we break it up into an integration by parts. So we say u equals e to the xy du equals y e to the xy dx. V equals, and we're going to choose sine of 2x, and dv equals 2 cosine of 2x dx. And in the end, when we solve this integration, because we have to go at it twice, we end up with, by using this kind of a method, which it's just tedium writing it out, you're going to end up with e to the xy cosine 2x dx is equal to y e to the xy on y squared minus 4 times cosine of 2x plus 2 sine of 2x. I may go through the integration as a single video sometime, but for right now, I'm leading you through the integrations, And so you have this first result. And it's useful in a couple of ways, because there are some integrations where we treat y as a constant. For example, up here. So this result is useful to that top integral. Now, the more difficult integration by parts is this integral, the one right here, this middle term. We have x, y, y, e to the x, y, cosine 2x dx. And that's going to take a little bit more doing. In that integral, get that straight. In this integral, we again integrate by parts. U is equal to, oh dearie, U is equal to x e to the xy du, of course, is going to be e to the xy plus xy e to the xy dx. V we choose to be cosine 2x, and dv equals minus 2 sine 2x dx. And we do that substitution, we do our u v equals u dv plus v du, and whatever iterations we go through, we get a solution. And this solution, where is that? Yes, where did I? Well, anyway, you go through that. I think I combined those solutions, recognizing okay. I ended up with this, that x e to the xy cosine 2x minus y e to the xy, I hope I did this right, y squared minus 4 times cos 2x plus 2 sine 2x is equal to x y e to the xy cos 2x dx minus 2 x e to the xy sine 2x dx. And it was this result that I used to solve those integrations, you'll see that you can substitute into this into the solution so that you don't have to go through as many integrations. And when you recognize that, you end up with an H prime. I mean an H prime of y, it's going to be long, is equal to x e to the x y cosine 2x minus 3 minus, and let's give myself some room here, clear this up. Again, I just want you to recognize that I don't want to keep it too messy. Alright, so we have y e to the x y over y squared minus 4 times cos 2x plus 2 sine of 2x plus x e to the xy cosine 2x minus y e to the xy y squared minus 4 cosine 2x plus 2 sine 2x, and that's our h prime. And you can see these two terms cross out, and this term and that term cross out, and you're left with h prime equals minus 3, which means h of y equals minus 3y. And the solution to the problem is, okay, that's the h prime, so that's 1, 2. Where's the third sheet? This is the beginning of, I had 4 sheets for this problem. Oh, yes, here we go. After we do all those integrations for both f and h prime, we end up with a solution of e to the xy cosine 2x plus x squared minus 3y, which is h, equals a constant. So this ends up being our solution to that differential equation. You're going to have to go through the individual steps yourself. I've kind of led you through the approach where you take integration by parts. You look at each integral for f of xy and h prime of y. And you see you've got 6 integrals that you've got to solve. And some of them are similar, like I said. In some cases, you treat y as a constant, and the integration is similar to the v substitution that we made here for this integral. So we can use that result sometimes a couple of times, and this result for this substitution here. So work it out, try to work it out yourself. I'm going to make a separate video for that solution because it is so long. 4 sheets of paper for me with my handwriting to solve it. My handwriting isn't the most economical. There are other problems. I think we've spent a lot of time on this. I could go through more. There are 15 problems altogether. Maybe we'll do them in another video, but I think you've got the gist. We recapped the 4 methods that we've looked at so far. We have another method. We're going to be looking at get all my papers here. We're going to be looking at, I think, one last topic before we move out of this chapter, and that is called Homogeneous Equations. Integrating factors. We're going to look at integrating factors and homogeneous equations, and we'll be done. This will be finished. We're going to be looking at applications, first-order equations, and, for example, radioactive decay is a big one, and we're going to be looking at other problems. Radiocarbon dating is another interesting area. Let's see if there are any others. Mixing, I guess. Here's one. Yeah, I think the mixing problems are first. Yeah. Yep. I think these are first-order differential equations. So we're going to look at a couple of examples. And then, are there any others? There's another pendulum, elementary mechanics. All right, we're going to look at elementary mechanics, bodies with variable mass, which is interesting. And then the last thing was the existence and uniqueness theorem, which gave us the first approach, P of x and G of x. And this is a long proof. It's about 10 pages. 10 pages long. And then we move into second-order linear differential equations. So that'll be interesting. So we don't have much more to go on first-order differentials. We do have integrating factors, homogeneous equations, and applications. And that will be it. I'm not going to go into the uniqueness theorem. I think more people are interested in applying these results than proving. I don't know. Maybe I'll do an independent video on the proof for the uniqueness theorem. But again, that's only for one method. That doesn't cover everything that we've looked at. So anyway, I will be putting up more videos soon, and hopefully this has been helpful. Again, we've looked at 4 methods, and this one was pretty involved. I have to say so myself, and I will make a separate video going through the entire solution.